So far we have seen a general criterion to check invertibility of a linear operator in terms of inf-sup conditions, and we also have seen how to apply those conditions to some specific saddle point problems such as Stokes equation and the Poisson equation. Now we start discretizing the problems. So we start with the general setting. Suppose we have two Banach spaces, x and y, just like before, and we have bounded bilinear form. And the capital A is defined as before, sending x to y prime. And we're going to assume that capital A is invertible. We look at this problem, ax equal to b, and x star is going to be the solution of this problem. It can be written in the variational form in this way by using the bilinear form. Then we look at subspaces, closed subspaces, subspace of x and closed subspace of y. And we simply restrict this variational form into the subspaces x and y. So find x hat from this should be actually x hat here, x hat from x hat that satisfies this equation where the test function is now restricted to y hat, and this is of course the Galerkin problem. Note that it is obviously x hat does not need to be equal to y hat, so that's why this setting is called Petrov-Galerkin setting. Now, if you look at this continuous problem, and since this equality is satisfied for all y from capital Y, in particular it is satisfied for all y from y hat, and we subtract that from this equation, we will get this equality that says that the difference between the true solution and the Galerkin solution is in some sense orthogonal to all elements from y hat, and orthogonality should be with respect to this bilinear form A, and that's called Galerkin orthogonality or Petrov-Galerkin orthogonality. Okay, so if you look at now this discrete problem, we can apply exactly the same conditions as we applied to the continuous problem, in particular the inf-sup conditions. So for example, well, one of those conditions would be this condition here, that's the inf-sup condition, or it would be the bounded below condition for the operator A hat. So this would be one of the necessary conditions for invertibility. The other one would be injectivity of the transpose of A hat. So this is one of the discrete inf-sup conditions. So supposing that this is true, now we want to look at the error between the error of the Galerkin solution. So we look at the error of the Galerkin solution by using the triangle inequality. We can write this. So we are just simply considering the arbitrary vector from x hat, and by using triangle inequality we can write like this. And if, since x is in x hat now, this difference is in the discrete space x hat, so we have x minus x hat in x hat. So we can use the inf-sup condition that we just described here. Now consider x minus x hat instead of x. Then we see that this difference is actually bounded from above by that supremum with 1 over alpha hat in front. Then we use Galerkin orthogonality to replace x hat by x star, because x hat minus x star is orthogonal to y hat, capital Y hat, with respect to this bilinear form. then at that point we can actually just use the boundedness of this bilinear form to have this inequality. So that gives us Sear's lemma for Petrov-Galerkin methods. Because x was arbitrary element of x hat, we get the error of the Petrov-Galerkin method is quasi-optimal, meaning that it is bounded by up to some constant, bounded by the error of the best approximation from the x hat. And let's look at the constants here. Here we have just a norm of the operator or norm of the bilinear form A. So this will be, once the problem is fixed, this constant is fixed. Now this alpha hat constant will depend on this discrete space x hat. So we think of this as some finite element space, and y hat. So it depends on these two discrete spaces. And usually we are talking about sequence of approximation spaces, sequence of spaces x hat and sequence of spaces y hat. And we don't want this y hat to degenerate to zero in along that sequence. So generally we want this alpha hat to be uniformly bounded away from zero, and then we're going to get this constant independent of the subspace that we are using, and we can really say that the approximation is quasi-optimal. Okay, so now we considered this inf-sup condition so far. That's the bounded below condition for a hat. So what is a hat? A hat would be, because you see that this x and y are restricted to x hat and y hat, this operator a hat is defined by just restricting x and y into x hat and y hat. Then this inf-sup condition, you can see that is simply equivalent to the bounded below condition for a hat, or it is in turn it is equivalent to injectivity and range closeness. And usually in applications we are talking about finite dimensional spaces here, these finite element spaces. So range is automatically closed. So this is really in the discrete setting, it's an injectivity of a hat operator. Now of course we want to have the discrete problem well posed, or we want to have this discrete problem here that gives us discrete solution. We want the corresponding operator to be invertible, or the corresponding operator for this is of course a hat. We want a hat to be invertible, so that means we need the other inf-sup condition also. So that would be that condition where now we have the inner supremum has oh, there is some mistake here. So we want to have inner supremum over x and outer infimum over y, right? So we know that this condition is of course also equivalent to the injectivity of the transpose of a hat, or it can also be written in terms of the bilinear form in this way. So we need these two conditions for the invertibility of the discrete operator a hat. Now we can look at the error estimate in terms of this operator a hat. So let's recall our Galerkin problem. So here it is, and a hat that we just defined. Now we can write this here, where when x is restricted to x hat and y is restricted to y hat, by using the canonical injection operators. So here, for example, this Jx is going to be sending x hat into x. This is just the injection operator. So we can put those injection operators here, and then we can take the injection operator jy over to the other side, and it will become the transpose of the injection operator. So a hat is really, we can write a hat also in this way, with injection operator here and the transpose of y, injection into y on the other side. Similarly, here we can also write it as b composed with injection operator jy applied to y. So this composition, so I write here, this is simply the transpose applied to b, right? Transpose of the injection operator applied to b. So the Galerkin problem now can be written in this way here, like this. And in operator form. And we write b, of course, as ax star with the exact solution x star. Then now inverting a hat, supposing that a hat is invertible, now the Galerkin solution can be written in this way here. A hat inverse applied to the injection, transpose of the injection operator jy, a, and the exact solution x hat. And whatever this operator that is in front of x hat, x star, that is called the Galerkin projector. So this projector takes the exact solution and sends it into the Galerkin solution. It's a projector because if you take an element of x hat and you apply the Galerkin, this operator p hat, then you will see that because x is an element of x hat, we can write it here with the injection jx, and you can see that this is just a hat. So we get x back. So this is indeed a projector. Okay, so once we have this projector, now we use standard methods to evaluate the error. So exact solution minus the Galerkin solution can be written in this way with the Galerkin projector. And because this is a p hat is a projector, we can now stick in minus x and plus x and write plus x as p hat applied to x for any it's important that x is now in the discrete space x hat. Okay, so we group them like this way, and we can see that this is actually equal to I minus the identity minus the Galerkin projector applied to the exact solution minus the this arbitrary element. And because x is an arbitrary element, we will immediately get this bound. And again, it's a quasi-optimal bound with the constant given by the norm, operator norm of the identity minus the Galerkin projector. Now, if x is a Hilbert space, then there is an identity called Kato's identity that says that for any projector, the norm of the I minus projector is equal to the norm of the projector itself. So this will simply become the norm of the projector. We can also evaluate the norm of the projector. So the Galerkin projector is simply this combination, and that's bounded by the norm of the inverse of the discrete operator A times the norm of A. So you can see that here, this generally we want to have the norm of the inverse of the discrete operator uniformly bounded. Now, in general, when X is not a Hilbert space, we can bound this by just 1 plus the norm of the Galerkin projector. So in general, we're going to get this CS lemma that we already actually derived this by other method, right? So that this was simply 1 over alpha hat. The norm of the inverse of the discrete operator a hat and also the alpha hat, so these are related to each other. To check this is uniformly bounded, we need to look at the discrete inf-sup conditions. So remember now, norm of that is equal to 1 over alpha hat, where alpha hat is this inf-sup condition for a hat. Now first, if you have a coercive problem where this bilinear form is coercive, it's very easy to check this condition. So x is equal to y, and suppose that we have this coercivity condition. Then we take x hat equal to y hat. Of course, we don't have to take it, but if we take x hat equal to y hat, it will be easy to derive the coercivity constant. The inf-sup condition. So obviously, because A is coercive on the whole space X, it is coercive also on the subspace X hat, and the coercivity constant for the subspace will be not worse than C. So you can imagine that if this X hat is very small, you might actually get even better constant. But all these constants will be bounded below by this continuous coercivity constant. So the discrete operator a hat is invertible with alpha hat constant at least equal to C. So that means we don't really need to check anything if you have coercive problems, and if you take the trial space equal to the test space in the discrete problem, meaning that we are just having pure Galerkin setting, not Petrov-Galerkin setting. So we say that any subspace is inf-sup stable in this case. Now the next case concerns saddle point problems. So for saddle point problems, we have the two spaces are equal to each other, but they have this special structure V cross Q, and also the problem has this special structure, right? Actually, strictly speaking, we will only have saddle point problems when this bilinear form A is positive, but with slight abuse of terminology, we are also calling this general problem saddle point problems. Okay, so to discretize this problem, we take subspace of V and a subspace of Q. Okay, they should be closed subspaces in general, but in practice we only take finite dimensional spaces. So this is automatically the closedness condition will be automatically satisfied. Now we know that in order to ensure that the discrete operator is invertible, the discrete operator corresponding to this problem and these subspaces, what we need is A0 hat is invertible and B hat prime is bounded below. Now B hat would be just B restricted to the discrete spaces, V hat and Q hat. It is defined by this bilinear form B. And also we have A hat, right? A hat would be just, again, the bilinear form A restricted to V hat, the discrete space. And further restriction of A hat, which is A hat 0, that would be now basically A hat itself restricted to the kernel of B hat. And recall that we need invertibility of this operator here for the invertibility of the discrete operator corresponding to the saddle point problem, and we need bounded below condition for b hat prime. Now, usually in practice, we will have this a positive, and checking the invertibility of a hat 0 will not be very hard. The important condition to check is actually this condition. So that condition now we can write by using an inf-sup condition in this way. Inf-sup condition for the bilinear form B. So this condition says that for any given P from Q hat, basically it says that there exists some V in V hat such that this inequality holds, where beta is, of course, this should not depend on P. And this you can call discrete inf-sup condition. Now, of course, since we are solving this saddle point problem, we can assume that we already have this condition, the continuous inf-sup condition. Now, look at the difference between discrete and the continuous inf-sup conditions. The continuous inf-sup condition says that for any given P from Q, there exists V in V that satisfies this inequality. So you see that the discrete condition, the discrete condition says there exists V in V hat. So it has a smaller set of V's to choose from. That means, intuitively speaking, if you have this V hat large enough to include all the relevant, say, V's that come in the continuous inf-sup condition, then the discrete inf-sup condition would be satisfied. Now, on the other hand, say V hat is fixed. If you make Q hat smaller, then you also might have this condition satisfied. So the discrete inf-sup condition basically wants the V hat to be big and Q hat to be small. There are many ways to check this discrete inf-sup condition, and one very nice way would be to go through this approach called Fortin operator. Linear bounded operator sending V to V hat is called Fortin operator if it satisfies this condition. So for any V you apply the Fortin operator, you're going to get basically a discrete version of that V, and apply this bilinear form that would be equal to the bilinear form applied to the original V for all Q from the discrete space Q hat. In other words, you can also say that this diagram commutes, where now B is the operator defined in terms of the bilinear form B. So B sends V to Q hat, and Fortin operator sends V to V hat. Then the discrete version of that B operator, B hat, sends V hat to Q hat prime. So that would be over here. Then so applying Fortin operator and then applying B hat is over here, is same as applying B and then applying the transpose of the canonical injection of Q hat into Q. Okay, so let me show you how you can now prove the discrete inf-sup condition if you have a Fortin operator. So if you have a Fortin operator, then this equality is true. I did not change anything because it's just in the denominator. Then we apply the boundedness of the Fortin operator over here. So overall we have this inequality. Now let's look at what we need in the discrete inf-sup condition. So in the discrete inf-sup condition we need to bound this from below, and here this V hat is over all, small V hat is over the capital V hat. Then we can actually replace this V hat by Fortin operator applied to V, so that we can write like this way. So basically we just replaced V hat by pi V, and this will be smaller because it is basically what we are doing is we're restricting, instead of taking the supremum over V hat, we are taking the supremum over the range of the Fortin operator P, right? Then now we apply this inequality that we proved, that is here. So we have lower bound. Now at this point we see that the supremum is over the whole space V, and we can now apply the continuous inf-sup condition. So by the continuous inf-sup condition we had lower bound beta times P. That's actually true for all P, not only for the discrete for P from Q hat. And there is this the norm of the Fortin operator appearing. So if you look this inequality in the beginning and end here, we have the discrete inf-sup condition with constant given by the constant of the continuous inf-sup condition divided by the norm of the Fortin operator. So again, generally we want to have the norm of the Fortin operator to be uniformly bounded. In the next lesson we will look at some examples where we use Fortin operator to show discrete inf-sup conditions.